Hello, Stardust Explorers. Welcome back to Stardust Discovery. And today, with the Astro Princess, myself, we will be continuing to answer some of the physics questions that we started using the 2021 Physics WASSCE examination past question. So, last time we started the second part of the theory question, and we have solved the first two parts, question 8a and b. The last one, the question c part, involves satellite orbit equation. So understanding satellite orbit motion is what this video will be all about. And then I would read out the question. A satellite of mass orbits the Earth of mass. So you notice the difference in mass. So satellite is a smaller object compared to the Earth. So small m, big M, with a velocity v at a distance r from the center of the Earth. The distance r is similar to the radius of the Earth. Anyways, derive the equation between the period of the orbit and r. So this question is asking that you derive the relationship or the formula between the period of the satellite and the radius or the distance between the Earth and the satellite. Okay, so in order to understand the question, you need to first of all understand satellite motion. So I have put up this picture by the side to help us understand what this question is about. So typically, imagine the Earth. The Earth has a mass, big M, and normally the Earth has a radius. That is the distance from the center of the Earth to the surface where we are all standing on. Remember that we are on Earth, we are not inside, we are on Earth, so we all are standing here. So whichever part of the world you are on this. So there is a depth from the center of the Earth where we know the molten magma is, right, all the way to here. Okay, so that should be the radius of the Earth. Then for you to be able to launch a satellite into space and let the satellite orbit the Earth, that means you have traveled certain distance away from the Earth, and that is best described by the X here. So you see the additional distance to the surface, so that gives you the height above which the satellite is. So that means now that if I want to get the entire radius, it will now be the addition of the radius of the Earth plus that X. So that gives me the entire distance from the center of the Earth to the satellite. Okay, now this satellite is orbiting the Earth. It has a mass m and is orbiting the Earth at a velocity. Now this velocity has different aspect of it, which we are not going to get into, but you notice that is curving round, making that circular motion. Okay, so that is very useful for answering this question. Okay, so if you grasp that concept, then it makes sense to consider the centripetal force as an active force involved in this motion. So centripetal force is an active force we must consider. And what is the equation for centripetal force? Mass times square of the velocity all over the radius. Now, for the sake of this equation we want to solve, we would like to keep it simple. So instead of having the radius plus x, I will just take it that we are only dealing with x. The entire distance is radius. So instead of r plus x, we'll just deal with r, assuming that the entire distance is r, just for simplicity's sake. Okay, so we are trying to derive the equation. Remember, we are taking time to understand the equation so that we'll be able to come up with ways to get this relationship. So we have established the diagram that help us to conceptualize what this equation is about. So now we have that. We are now in the process of figuring out the forces at play, because the forces at play will help us to get the relationship. We mentioned centripetal force because this is the force that enables an object to move in a circular form. As we can see, the satellite is moving, I mean, not perfectly circle, but in an elliptical form, so it's moving around the earth. That is centripetal force in action. Now, because the earth is involved and the earth exerts a gravitational pull to any object close to it, including that satellite, that means that we need to consider the gravitational force of the earth. So, I mean, even the satellite has its own gravitational force, but because the earth is a much bigger body, the gravitational force of the earth will be stronger than that of any other object close by, because the earth is bigger. So that leads us to the other force involved. Now you see that I've trimmed down this diagram to look like what we will be dealing with. So take this as an example for solving this equation. However, there will be cases where it will require that you do the actual distance, then involve the x and all of that. But for the sake of this, you can keep it simple, just like in this diagram. So when you think about the Newton's gravitational force acting on the satellite, and you think about the centripetal force required to keep the satellite in circular orbit, what comes to mind? You can equate these two forces to get whatever parameter you are looking for. So these two forces has radius, one of them has velocity. So if I want to get the velocity, I need to equate the two forces for me to get it. So with this in mind, we are going to see how we can derive the relationship between the radius and orbit with the two equations. So if you look at the two equations, there are some things that are common. You can cancel them out, the small masses and one of the radius. So when you do that, you will get equation 1. Okay, so looking at equation 1 and thinking about it, remember that we are looking for period. We already have radius in the whole thing, but we do not see period yet. So how do we introduce period in this equation? Now you have to recall that the period of an orbit is related to the velocity of the satellite and the distance r, according to the equation I just showed. This equation here, v equals to 2 pi r over t. This is a very important equation where v is the velocity, r is the radius, and t is the period. So if you take this equation and put it into the equation 1, that will give us this equation 2. So everything's still the same, you just substituted for the velocity and you now have the period in the equation. Now we are going to open up this so that you have 4 pi squared r squared all over t squared. Okay, so this becomes your new equation. So this is what we have. Now you can see the radius, you can see the period. You have the two relationship looking at you. So to make it easier, you should rearrange this and solve for t squared. So if you rearrange this and solve for t squared, it will give you the Kepler's third law relationship. And that's where I started from the very first, to tell us that the relationship can be obtained using Kepler's third law. So if you go and state just the Kepler's third law, you did not solve the equation, because the equation required that you derive. Did you see that? Derive. So just stating the Kepler's third law as your final answer is not complete. Maybe you can get 1 mark, but if this question has 3 marks, you lost a lot of mark already. So be sure to listen to the question or read the question properly and follow the instruction. So the instruction here says derive the relationship. So we want to see a step-by-step derivation from, beginning from the first principles, the laws, and we want to see how that led you to the relationship we're talking about. So what I mean, when you get to the end, just like we have done, you can now state the law at that point. So actually, when you realize that this is Kepler's third law, you can simply state it. It states that the square of the period of orbit of a celestial body is directly proportional to the cube of the semi-major axis of its orbit. This semi-major axis is similar to the radius or the distance that we call r here. That's the semi-major axis of the orbit. So to state the equation, you can also state the law to get to boost your grade. However, the derivation stating Newton's gravitational law, stating the force that is involved, stating the centripetal force, this gives you 1 mark each, independent on the full mark assigned. It could be half marks. Properly getting the derivation up to this point, we give you another 1 full mark, because introducing the v equal to 2 pi r over t is key to getting your final answer. So if you're able to introduce that, that gives you another half mark, and your ability to successfully open up that bracket until you get to the Kepler's third law will guarantee that you successfully answer this question. Okay, so you have to take your time carefully and carry the exponentials along without making mistakes. When you are rearranging your equations, making one of them search for the formula, carefully do these things with your knowledge of mathematics, and you should be able to excel in this question and get your full marks. Okay, and there we'll end this for today. I hope this wasn't too complex, and yeah, you can always check back with your textbooks. Maybe you have a different method of solving this. There is no wrong method, in as much as you get to this relationship. That's all that matters. That's still fine. But remember that the procedure is where the answer is, the solution, the step-by-step work. So do not give just a one-line answer for this type of question. Okay, and then I will leave it at this, and I want to remind you that you may not look like where you're headed right now, but a better version of you is emerging. And I will see you in our next one. Do not forget to subscribe, comment, like, and share this video. Okay, take care. Bye.